particular worksheet, a lot of the information on the test will be very similar to the test, so you can practice these problems. So when you read a problem, remember what this is in a survey for college graduates. So right there, when you see a number out of another number, you know you're dealing with a proportion. That's your key right there. Because here's the thing, you've got to be able to read these problems and know which set of formulas am I going to? What am I actually dealing with in this problem? This is clearly proportions. Some number out of another number is a proportion. Now, do we have one or two populations? Well, we've got our college graduates. That's certainly one population. And then we have without a college education. So we're going to call this one population 1 and this one population 2. Whenever you're dealing with two populations, you need to define which population is which, because that's going to tell me how you set up your hypothesis. Please make sure you do that. Have two of them. Tell me which one you're calling number 1. Tell me which one you're calling number 2. Okay? Now let's read the question. At the 5% significance level, do the data provide sufficient evidence? Right off the bat, that's a hypothesis test. It's not asking for a confidence interval. So now you know you are doing two sample proportions hypothesis test. So when you go to your formulas, stop yourself. Let's, so you can narrow down where you are. You're doing population, and see this one is just for 1. So you have to come down until you get to 2. Let's read a P1 search. No, it's P1. P2. So this is the formula that we're going to use. Here's how we're going to get our screen in there. Okay. All right, so let's set everything up. Now that we know we're doing a hypothesis test, let's start with the null. Always have your null is whenever you have two proportions, your null is going to be that those two are equal to each other. Notice we don't put the hat on them because when we're doing our hypothesis test, we are strictly dealing with talking about the actual populations. Now, for our alternative, we have to now read that question. Just to conclude that college graduates are more likely satisfied than those without. So that means our proportion for the college graduates, which is our P1, is going to be greater than P2. You need to read this carefully. Don't just assume the word more likely means you have to put a greater than sign. You got to determine what did you define as P1, what did you define as P2. So in this case, P1 is greater than P2. All right, now that we have our hypothesis set up, we need to find our sample information. So let's start with P1. When we're talking about the sample, now we're going to use the P1 hat, because that's going to represent the information from that first sample, which is our college graduate, which is 84 out of 185. Go ahead and take that to 3 decimal places. I believe we get 0.454. And then we're going to do P2 hat, and that's going to give me the 76 out of 180. Again, go to 3 decimal places. Keep in mind, you do not want to round too much until you get to the very end. Keep your numbers 3 to 4 decimal places while you're working out the problem. All right, now we need our pooled. We're going to pool these two together. One thing about a pooled proportion, it's going to be in between the two that you're pooling. So if you get a number that is not between 0.422 and 0.454, you made a mistake somewhere. And if you don't remember how to pool them, go back onto your formula. It's actually at the bottom of this column, and there it is. Your PP hat is x1 and x2, and then n1 and n2. So when you add 84 and 76, you get 160. And when you add 185 and 180, you get 365. So our pooled is 0.438. Now we have all the information we need to plug into our formula. So again, you go back to your formula sheet. Oh yeah, here it is. This is the one with two populations. We're going to subtract them. We're going to do the pooled times 1 minus the pooled, take the square of that, and then the 1 over n and 1 over n2. So let's go ahead. Regardless if you're going to use a graphic calculator to calculate this, meaning you're going to use the statistical apps on your graphic calculator, I want to see the formula written out. So here's the part I want to see to get full credit for the problem, and that is I want to see P1 minus P2. Sorry, I wrote 454 minus 0.422 over. This is going to get messy, so it's 0.4381 minus 0.438. There's your PP hat, parenthesis 1 minus PP hat. This other one is a completely separate radicals. We have 0.1 over, what is n sub 1? Go to p sub 1, it was 185. And then 1 over 180. Now at this point, if you want to utilize your graphic calculator and go ahead and use the app, you go to Stat, Test, you're doing a 2 proportion z-test. You can do that. You will get a number of 0.613 approximately. If you're going to work it out, be careful, all right? I'll work this particular one out so you can make sure you're doing it correctly. When I do the first radical, I get 0.246. When I do the second radical, I get 0.0110. Because it was like 0.01, then there was like an 096, and that goes no. This became, at the bottom, I believe it was 0.052 and 0.615. Again, if you use the calculator app for a 2 proportion z-test, I believe you get 0.613. That is okay. Calculator is actually going to be a little bit more accurate. If we had pulled all these numbers out to 4 or 5 decimal places, we would have been closer to 0.613. So that is your test statistic. All right? That is the test statistic, that 0.615 or that 0.613. All right, I'll use 0.613, doesn't matter which one you use. Now, we have to determine if that test statistic provides sufficient evidence. The sample provided sufficient evidence to conclude that the college graduates were more likely. To do that, you can run a p-value or a critical value approach. P-value approaches are pretty easy when you're dealing with z-scores, because with a z-score, you can look directly on the table. I would always suggest a picture. I always like pictures. This is a right tail test. All right, when you are doing a p-value approach, you put your test statistic down here. Your p-value is the area in the tail. So to get that area, what are we going to do? So we're going to use the 0.613 again, 615. Your p-value will be slightly different, no big deal. You would not take all the points for that, of course. So go to your, this is a z, because again, how do we know it's a z? Right there, z-test. Sorry about that. Let's go to our table. You go to your table, and we are looking at 0.613. Well, if you come over here, you're only going to get to about 0.61, all right, which is 0.7291. Of course, that 0.7291 is this side. This is also why you draw a picture, because remember, the whole area is a 1, so when you see 0.7291, you're not going to make a mistake and call that your p-value, because clearly the p-value is smaller than that. In fact, it is going to be 1 minus that. So 1 minus 0.7291 is going to give me 0.2709. So our p-value for this problem equals 0.2709. Either way, alpha is 0.05. P is clearly greater than alpha. This is the reasoning. These are the steps I should see. So I know you understand what it means to reject or not reject. You can only reject if your p-value is very small, meaning the probability that you would get the result you got, if the null hypothesis were indeed true, has to be so small that that null hypothesis must be false. So how small is small? Well, some of you might think, hey, 27% seems pretty small, but it's not. 0.2709 is clearly smaller than that. We would need something lower than 5% to reject that. In fact, we have almost a 30% chance of getting the results, even if they were equal to each other. Because when you sample, you know, you could have that. The sample just turned out this way. It's fine. So you have to write your interpretation. Remember your interpretation. I'm going to go ahead and erase what we have here. We know we are rejecting. Our interpretation is going to come from that question we were asked in the beginning. In other words, here it is. At the 5% significance level, do the data. Remember, this was a do not reject. So we say the data, get all this, get rid of the do, get rid of the question mark. The data do not provide sufficient evidence to conclude that the college graduates are more likely. And yes, when you write that interpretation on the test, I need to see you write it in context of the problem. Many of you on that first test, I went through and rewrote a lot of your interpretations for you so you could see the way they're supposed to be set up. Okay? Since we have gone through number 1, number 2 is very, very similar. It uses the same formula. So what I'll do is make sure you have everything set up correctly. We'll just set the hypothesis up. It'll allow you to do the calculations on your own because you have the formula. You have the answer key back. So here we have of 85, randomly selected women 38, have tried some form of alternative medicine. 90 selected men, 23. Again, 2 populations. We'll call the women P1. We'll call the men P2. Okay? At the 1%, do the data provide sufficient evidence to conclude that women are more likely? So again, a very similar problem. I'm not going to go through this full one. P1 greater than P2 for your alternative. And if you check down here, you can see, you can set it up the same way we did the other problem. And here we have a test statistic, and this time they did a critical value approach. Keep in mind when you do the critical value approach, this one's a little bit different. It's still a right-tailed test, so you draw a picture of a right-tailed test. But this time, you need to find the critical value. All right, here's how the critical value is different. You don't put your test statistic here, you put your critical value there. So to get that critical value, you need your alpha. In a critical value approach, we set this area as the alpha, which is 0.01. You can go to your stat formula page, and if you actually, instead of going through that whole chart, if you go to the end of the t-table, you have a quick sheet to tell you what a z of 0.01 is. So a z of 0.01 is about 2.326. They rounded it 2.33, doesn't matter. And then, what you do is you mark where your test statistic falls. Think of this, of course, as a number line, 0 in the middle. Then it goes negative and positive. So where is 2.66? It's going to be over here. The tail is your rejection region. This is your do not rejection region. So this one would be and reject. Okay, but you should go through it, practice it, and make sure you get all those values. Let's take a look at what's next. Here we have so to determine what you actually have in this problem, again, look at the information you're given, and then look at the question you're being asked. Here it's very simple. The data provide enough evidence the current distribution of military personnel differs from the 1985 distribution. Whenever you're comparing distributions, it's always a chi-square goodness fit. So remember that, because you're not always going to be given this information at the top that kind of tells you what to do or tells you what kind of problem it might be. You have to read the problem and kind of make that determination. So how do you know? Here we're given two distributions. The U.S. Department of Defense provides data on the military personnel for 1985, and then a sample of 325 military personnel currently on active duty. And here we have, from that sample, how many were Army, Navy, Marine Corps, and Air Force. So again, two distributions is always the goodness of fit problem. So what does that mean? Go to your formula sheet. We're doing a chi-square procedure. Your goodness of fit is this first one, okay? Your chi-square formula is the same regardless if you're doing a goodness of fit or a test for independence. In this particular problem, you know, again, the formula is summation of observed minus expected squared over E over expected. Please make sure you know, if you're looking at a formula and you don't know what O and E stand for, that's where you run into issues when you're taking the test. And this is where you don't get your test done in time, because you're trying to look this information up while you're taking the test, and well, you're not really supposed to be doing that. So you have to know, okay, chi-square goodness fit is all about current observed values matching expected values. How do we find expected values? Well, you take the number times the percent. So let's go back to our problem and see what that means. Clearly, the current sample is what you are observing. These are our observed values. Of the 325, we've got 102 in the Army, 101 in Navy, 40 in the Marine Corps, and 82 in the Air Force. That's what we're currently observing. When we set up our hypothesis test here, okay, and you're comparing two distributions, your null is always, they're the same. We're going to go in with the assumption that the military distribution today is the same as the one in 1985. And you're going to write that statement. Okay? Your alternative is always what's being asked in this question. Your alternative is they're different. So for HO, you rate the distribution today is different. Sorry for my sloppy handwriting. It's not easy to write on these computers. Okay? Simple. In goodness of fit, distributions are the same as always your null hypothesis. We're going to go in with the assumption they're the same. We're going to see if our data provides us evidence to state they're different. How do we do that? We need observed and we need expected values. Here's our observed. This is what we observed today. The expected comes from, okay, what if they were the same? If this distribution matched what it was back in 1985, and we had a group of 325, remember, E equals N times P. So our expected values, well, for the Army, it would be 325 times, what's the percent? The percent was 36.3%. That's 0.363. So you're going to take 325. times 0.363, we would expect to see, we're going to take it to 2 decimal places, 117.98. Obviously, we can't put 98, but we're going to leave it that way for our math. And you're going to do that for each of them. Remember, you're getting your expected values from up here. You're not multiplying the percents by these numbers. You're multiplying the percents by the total of 325. So Navy is going to be 0.265 times 325. 0.092 times 325. 0.28 times 325. You do not use your observed values to find your expected values. All right, so go ahead and get all the calculations. This is the expected values. If the distribution was the same, of those 325, we'd expect about 118 to be Army, about 86 to be Navy, 30 to be Marine Corps, and about 91 to be Air Force. Obviously, we don't see that. It is different. It's different enough. Is this small sample different enough to make a conclusion that the entire distribution was clearly there's way more than 325 people in the military? Is the entire distribution different from 1980? So to do that, we bring in our chi-square formula. I like to do it using a chart. You can do it however you want. All right. We have to sum up some numbers. What are we summing up? Well, we're summing up the observed minus the expected squared divided by the expected. So I'm going to go through and do each of those. So what are we looking at? We would take our 102 minus 117.98, square it, divide it by the expected, and get an answer. So I want you to go through, hit pause, and find all four. So if you calculate all those O minus E squared divided by E values, I get this number. Of course, for the formula, we're going to sum them, and that's where we get our point of 033. This is your test, your chi-square test statistic. When we talk about the test statistic, it's going to equal the 9033. So we're looking at a 5% significance level. Sorry, I forgot I was on a chi-square. So for the 5% significance level, we have our chi-square distribution. We have 9.033, right? 9.033. This value here is going to be our p-value. So what do we need? To go to our chi-square to get an estimate for our p-value, you have to know your degrees of freedom. For your chi-square, your degrees of freedom are simply C minus 1. C is the number of possible categories. So we had 4 categories, right? Army, Navy, Marine, Air Force. So 4 minus 1 is 3. We have 3 degrees of freedom. We're going to look for where 9.033 falls on our 3 degrees of freedom. So go all the way down to your chi-square chart. It's that little one there. It's right there. There's your chi-square. We're going to go 3 degrees of freedom. That's right there. And for 3 degrees of freedom, you're going to find where 9.033 would fall on the chart. It's going to fall right between these 2 values. So you look up. Looks like take the smaller value first. Your p-value is somewhere between 0.025 and 0.05. So that's how you're going to report your p-value. Remember, it falls between at 3. 9.033 would be right about here. So that means the area is between the 0.05 and 0.025. Take the smaller one first. So your p-value is definitely greater than 0.025, but it is smaller than 0.05. What is our alpha? Alpha equals 0.05. So this is the kind of, again, this is that thought process I expect to see on the test. So the question is, P is what compared to alpha? P is smaller than 0.05. Alpha is 0.05, so that means P is less than alpha. And if P is small enough, in other words, smaller than alpha, we can reject our null hypothesis. And we are going to reject. In this case, we were going to state at the 5% significance level, the data do provide evidence that the current distribution of military personnel does differ from the 1985 distribution. Number 4 and 5, we're still talking. This time we are asked. All right. Notice we're given these contingency tables for number 4 and number 5. And the question we're asked has to do with, is there an association? So for number 4, conduct an association exists between age and preferred music type. Number 5, we're looking at, is there an association between the color of a car, red, white, or blue, and whether or not the car has been in an accident. So anytime you see association, you are doing chi-squared test for independence. I'm going to pick one of them to go through in detail, and then you can follow the similar steps for the other one. I'm going to pick number 5. Okay, so we're doing number 5. So an association, your null hypothesis. This is where it gets a little bit tricky. When we do a test for independence, we are assuming first that these two things are completely independent, meaning whether or not a car gets in an accident has no dependence on the color of that car. So you can write that color and accident status, or whatever you want to call it, is independent, or you can write there is no association, because if two things are independent, that means they are not associated. So we can say there is no association between car color and accident. All right, it's a little sloppy, but you get the idea. So the alternative, of course, is yes, an association exists. Remember, your alternative always comes from that question that's being asked. So your alternative is yes, there is an association, or if you want to use the word independence, color of a car and whether or not it's in an accident are not independent, or they are dependent on each other. There are so many different ways you can write this alternative null hypothesis. You have to make sure you understand what's going on. There is an association. That means they are dependent on each other. Okay? Now, the formula is the same. We still find that O minus E squared over E and sum it up. So we need to find, and you need to figure out and identify what your observed and what your expected values are. Okay, this is your data. These are your 6 observed values. You've got them, 28, 33, 36, 23, 22, 30. We have those. What we need are the expected values. And this is where the chi-square gets a little tricky. So let's go to our formula sheet. And you really need to be relying on this formula sheet for everything. So go to your formula sheet. Let's go up to square. And here we are. Oh, expected is row times column divided by n. That kind of makes sense. It's kind of taking like a, if you look at the formula this way, which is the same formula, you took each row, you got the percent, and then you multiplied it by the column. So that this formula is kind of that put together. So row times column divided by n. All right, to do that, I don't need the formula anymore. You need to know what the row totals and the column totals are. So first, go through on your observed values and get those row and column totals. Go ahead and hit pause and do that. I got my row and column totals. I'm going to recreate this. first one. I'll do the first one with you, then we can hit pause and fill it in. We want to know what is the expected value. So we know that of all the cars, we have a total of 172. Just double check that your row and your column totals both add up to 172. So of the 172 cars that we observed, 28 of them were red and also in an accident. Okay? So the cars that were in an accident, 28 were red, 38 3 blue, 36 white. So this expected value comes from if there is absolutely no association, how many of the 172 would we expect to be red and in an accident? So you have to go to red. What's the row total for red is 97 times the column total, 51, divide by 172, and we get 28.8. Take it out one decimal point. Oh, so if there's no association, we would actually expect that number to be red and in an accident. Go through and do it for each of them. I'll hit pause, and finish out the chart. Remember, row total times column total. So here, I'll do blue with you again real quick. So blue and in an accident would be again 97, but now blue is 55. 97 times 55 divided by 172, I get 31. Okay, so go ahead and do it for all of them. So here I got my expected values. You can see they're very close. I would actually expect a small chi-square test statistic. They look very close. 28.8, 28, 31, 33. So these are your observed, these are your expected. Now this one gets a little tricky. There's a lot more calculations because now we have to take to get our chi-square test statistics. I'm going to do this one a little bit different. We have to take each of them observed. Start with the first one. Minus expected squared divided by expected. And then add that to the next one, which is observed, going across, minus 31 squared over the expected 31. And then the third one across is 36, minus 37.22 over 37. I took that into two decimal places. Now the bottom, so we have 23. Alright, and so on and so on, you do the next two. This is a lot of tedious work. On the test, there are some things I am not going to make you calculate. I will go ahead and say, hey, the chi-square test statistic for this problem is, let's take a look. Yeah, remember I said it's probably going to be really small. It's really small, 0.4287. Okay, so when you draw that, this is going to be a really big p-value. Really big p-value. Again, on the test, you only get 90 minutes, plus I give you the extra 30 minutes to make sure you upload your work correctly, which again, you get the work uploaded during the test or immediately after. If you turn the work in 24 hours later, it's really hard for me to accept it. Yeah, I'm going to get a really big p-value. This is a really small test statistic. Small test statistics yield really large p-values. But to get our p-value, we still need our degrees of freedom, so let's just double check that. You can go back, we're doing a test for independence. Row minus 1 times column minus 1 is your degrees of freedom. So it's going to be a 2 by 1. So degrees of freedom just equals 2. Okay. There are 3 columns, so 3 minus 1 is 2, 2 rows, 2 minus 1 is 1, degrees of freedom is 2, and I'm going to look for 0.4287. Go to your chi-square, erase line 94, let's do 2. Yeah, there is no 0.4, it's way off here somewhere. You see that? Look at what's happening to your areas. They start off small, and as you move to the left, they get bigger and bigger. So your p-value is actually larger than 0.10. It's going to be a big p-value. That's going to be really big. So p is larger than 0.10, which means if alpha is 0.05, p is definitely greater than alpha, and this is a do not reject. Okay, so I went through that one in detail with you. I'll leave you the other one to do. You've got the answer key there, but keep in mind on the test, these are very long problems. At some point, I'm going to give you some of the calculations. So please read the problem carefully. I might ask you to find expected values, but then I'll give you the chi-square. So if you take the time to find a chi-square, and I already give it to you, you've just wasted a lot of time. So just be careful on the test, okay? I want to move on and do the analysis of variance. I know this is a long video, but we'll keep going. Get this done. Let me erase this problem now. Okay, so question, oops, finish erasing, sorry. All right, so the question becomes, how do I know what type of problem this one is? What's going on? We're comparing a whole bunch of things. We're comparing 4 different brands of batteries. Data provides it to conclude a difference exists between them. And we're given all their means. Whenever you are comparing multiple means, more than 2, you are doing an ANOVA. Okay? Is there a difference between these 4 batteries? Okay, their battery life. So for the test, you are going to have to do one with what we call summary statistics, because I'm kind of forcing you to do one problem where everybody, whether you have a graphing calculator or not, are kind of all on the same page. Meaning you can't just plug the data into your graphing calculator and let them do all the work. You're going to set up an ANOVA table, and you're going to work out the problem using the formulas. And we will go through that. I certainly did a video of this. So for my ANOVA table, and remember when I explained analysis of variance in the other videos, what we're looking to, we're comparing the differences that exist among each of the brands. That's kind of the value of our numerator in our test statistic compared to the difference that exists within each. There's variances within each brand of battery within those samples, and there's variance among the samples. So an F-test statistic is really looking at if the variance that is among the samples is greater than the variance within the samples. The mean square of the treatment is the variance among the samples, and the mean square of the error is the variance within each sample. So if that variance is much greater among them, we end up with a larger test statistic, and then we end up rejecting. So what are we rejecting? Our null hypothesis, of course, that all means are equal. Okay? All are start with the assumption they're all the same. Yeah, we see brand C here seems a little bigger. We're just going to go with the assumption, or I'm sorry, brand B has a greater, it's a little bigger. We're going to go start with the assumption they're all equal. And then our alternative, sorry, is they're not all equal. Okay, there's a lot of different ways you can write this hypothesis as well. You can, for your null, state, hey, mu of A equals mu of B equals mu of C equals mu of D. But for your alternative, you have to say there's at least one difference, right? So, or you have to say they are different, however you want to state it. So the best way to work with an ANOVA to eventually get to this test statistic is to draw out your ANOVA table. I do believe I provide you with what an ANOVA table looks like to help you out. All right, we have our degrees of freedom. We have our sum of squares of the treatment. Okay, and then the sum of squares of the error. Remember, the treatment is what's the variances that's going on among all the data, and the error is what's happening within each one. And then, of course, down here you get your totals. So you have sum square, then you have the mean square. Okay, and then eventually you end up with your test statistic. So when you go to your formula sheet, this is where it gets a little tricky, because sometimes there are formulas based off data, where you are given all the data. We are given here, we call summary statistics. We're not given any data. Or there are formulas for when you're given summary statistics. Let's go to our formula sheet for a second. Okay. This particular set of formulas are defining formulas, and then these are computing formulas. The computing formulas are good if you're given individual data values, because you can see it in here. When you see a whole bunch of little x sub i's, that's an individual data value. Okay, we're not going to use that. We don't have individual x sub i's. What we are going to use is our sum of squares for the treatment. We're going to use this formula. We don't need x sub i's. Oh, we need an n for each category. We have a sample size for each of the 4 brands. We have a mean for each of the 4 brands, and if you're not sure what this means, just come up here. Oh, mean of the sample for population J, whatever population it is. And we need an x bar, so we got to talk about that for a second. And then for our sum of the squares of the error, we have an n for each of our samples, -1, and we have a standard deviation. So we're just going to use these 2 formulas right here. So let's start with the sum of the squares of the treatment. So for the sum of the square of the treatment, it's the summation of, remember, n sub j, x bar j minus x. So we have n right now squared, and then that's squared right here. Okay. So let's, well, we've got our n's, 8, 8, 10, 8. We've got our x bars, there they are. What we don't have is an overall mean. All right, you got to find an overall mean. How do you find an overall mean when you have sets of data and their means? You've got to weight them according to their size. So our overall mean, which is just our x bar, well, we have 8, 7.69s plus 8, 10.44s plus 10, 8.55s, and then we've got 8, 5.91s. Now here's a little trick. If the sample sizes were all the same, all we have to do is add those up and divide by 4, but since they're not the same, you can't do that. See, 8, 8, that's 24, 34. Okay, so you go ahead and get that, and that becomes 8.17. Okay, so now, let's go through each so we can get SS. This is SSTR, goes in this spot right here. We start with 8 times the mean minus the 8.17 plus the next one is an 8, the mean, minus 8.17. Use the same. This x bar over here is the overall mean. This is the individual sample means. This is the overall mean. Plus 10, 8.55. And this one has 4 sets. If I get a C on the test, I'll maybe only have 3. It's much easier to work with. So 3. And then 8, 5.91 minus 8 squared. So let's go ahead and calculate that. You can hit pause, figure it out. I get 85.37. That is our SSTR. Actually, these are the only two that are hard to find. Once you get those, the rest of the chart fills in very easily. I think I recall doing the problems. Okay, so the next one is for SSE. You go back to your formula sheet. There's SSE, summation, n minus 1 times standard deviation squared. So summation n minus 1 standard deviation squared. This is the J just means you're taking it from each sample. Oh, so the first one, 8 minus 1 is 7, 1.62 squared plus 7, 2.45 squared plus 9, because 10 minus 1 is 9, 2.52 squared plus 7, 1.30 squared. Okay, again, can pause, work it out. I get 129.37. So we need to, next, once you get those, that's the hardest calculation. Everything else just follows from the chart. So we need degrees of freedom. And if you're not sure degrees of freedom, come back to your formula sheet. Okay? Because to get MSTR, we have to take SSTR minus our degrees of freedom. So degrees of freedom for the treatment is K minus 1. And degrees of freedom for the error is N minus K. Okay, so the first one is K minus 1, where K, again, if you're not sure, is just the number of populations you have. So we have 4 minus 1, that's 3. And then N minus K, your total N was 34. We have, remember, we add up all the little N's to get to 34. Minus the number of populations, so 34 minus 4 is 30. Okay, so your mean square of the treatment is simply SSTR divided by degrees of freedom, SSE divided by degrees of freedom. So 85.37 divided by 3, I get 28.46. And then 129.37 divided by 30. And then when you come over here, your test statistic is MSTR, 28.46, divided by the mean square of the error, MSE, divided by 4.31. So you just divide those two values together, and I get 6.6 for my test statistic. So F equals 6.6. For 5% significance level, we draw an F curve, about like a chi-square. Let's do a critical value approach this time. And the table goes up to 30. It just dawned on me. But let's see. Here we go. My table doesn't go up to 30, and I will give you. I will make sure on the test that the table does go up to the values we have. Yeah. Unfortunately, our table goes up to 16. So we have to find f of 3, 30. I know the table on your formula sheet only goes up to 15. You can do a quick Google search, but again, finish or whatever one can be taken directly from your table. You can just honestly, if you type into Google F, comma, F, and then parentheses 3, comma 30, it'll give you the value. It's 2.92. So critical value approach means place your F's test statistic. There's our test stat is clearly in our rejection. Remember, on chi-squares and on F distributions, your rejection is always to the right tail. So that is a reject, and we kind of saw that. There's clearly a difference somewhere. But here's the thing. So yes, we would interpret at the 5% significance level, the data do provide sufficient evidence to conclude that a difference exists between the battery life of the 4 different brands. What an analysis of variance will not tell you is where that difference is. That's where you have to do a Tukey. I had showed you how to do a Tukey test on in StatCrunch. So here's a readout of the Tukey test for this particular problem, and we're going to try to figure out where differences occur. So the first thing they're going to do is find brand A and compare it to B. Does a difference exist between brand A and B? All right, well, let's look at the B value. So we're playing with the 5% significance level. So basically, we're looking for p-values that are under 5%. And it does not look like A. It's almost different with B. But it does not look like A is really any different from the 3 of them. And there's 2 different ways to determine this. One is look for a p smaller than 0.05. The other one is to look for a confidence interval that does not contain 0. Because when your confidence interval, so in other words, your lower is negative, your upper is positive, that means it contains 0. So there's a chance there's 0 difference. 0 difference, 0 difference. So A, no different from any of the other ones. So let's get rid of A and let's compare B to C and D. No difference between B and C. You see that? You see that? Ah. But look at this one right here. We compare B to D. 1, yeah, P is definitely smaller than 0.05. Also, look at our lower and upper limit. There is no 0. They're both negative. So B and D have a clear difference. And then finally, how about C compared to D? No, we're good there. So the only difference is B and D for that particular problem. Okay, so hopefully, oh, and there's the ANOVA table worked out. So hopefully this will help you as you're going through.